Hello everyone, welcome back to my channel. This is Jess. So today we'll be looking at another coding problem called word search. For this question, let's take a look at the question statement. You're given an m times n board and a word. You need to find if the word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. So just by looking at this problem statement, it seems pretty familiar, right? It sounds really similar to the question that I went over in my last video. It's called a number of islands. It's also counting cells in a grid that are horizontally or vertically neighboring. So if you're not familiar with this type of questions, I highly recommend you go look at that question first, because that will be an easier starting point. But if you are familiar with this type of question and you kind of already have an idea on how to solve this question, let's continue. Let's first take a look at an example. So you're given a board like this, and the word is A, B, C, C, E, D. And we need to find whether or not the word is in this grid. So we can see from the picture, it is indeed in the grid, A, B, C, C, E, D. And we notice that the same letter cell is not used for more than once, which means every single letter in the word that's given needs to have one single cell, just like this. So we can reuse the C. And let's take a look at another example. And so say if we're given this grid and you're given the word A, B, C, B, and let's see if this word is in the grid. We see there's an A here, and B is one of its neighbors, and C is one of its neighbors as well. But for this C, it only has these two neighbors that we haven't explored, even though one of its neighbors is B, but since we cannot use the same cell twice, so this way it's not working. And we see there's another A, but for this A, there's no other B's neighboring it, so for this example, the given word A, B, C, B doesn't exist. Since we've gone through a couple of examples, the solution to this question seems pretty simple. You basically need to traverse through the whole grid to find the letter cell that contains the first letter of the word, and once you've found that letter cell, you start to explore its neighbors. And then if one of its neighbors contain the next letter in the word, you then move to that neighbor cell and then keep exploring its neighbors until you've found all the letter cells in the word. But this solution contains a couple little points that we need to pay attention to. First off, since we can't use the same letter cell twice, we need to think of a way to keep track of whether or not one letter cell has been visited or not. And we also need to make sure that the letter cell is actually visited, meaning that that letter cell was used for matching a certain letter in the word, or not just being one of the neighbors of a cell that we were exploring to find whether this is the correct cell to match one of the letters in the word. Let's look at an example so that I can explain this concept more clearly. Let's say if you're given a board like this, and your word is C, S-E-E. And let's just start from this S letter cell for simplicity. So this S contains three neighbors, C, E, and E. And since this S contains two neighbors with the letter E, we are not sure which E would be the correct path to match all the letters in the word. So we're going to explore, say, the first E, which is the E on top of the S, to see if this is the correct path. So we move to this E, and we're going to mark this E as visited first, and we explore its neighbors. Since it only contains two neighbors, and the S letter cell is already visited, we're only going to go to its C neighbor. And we know that the letter after this E should be another E, and C is not E. So we go back to its parent, which is this E, and since at this point we already know this E wouldn't be part of the correct path to match all the letters in the word, so we mark this E back to not visited because this E is not used for matching letters in the word yet. So we want to keep it as not visited for future uses in case if this E would be a matching letter cell in later letters in the word. And this setting it as visited at first and then backtrack to itself after exploring its neighbors and then setting it back to unvisited, this process is called backtrack. Backtracking is a technique for solving problems recursively by trying to build a solution incrementally, one piece at a time, and removing those solutions that fail to satisfy the constraints of the problem at any point of time. So now let's go over the steps of solving this problem. Step 1, we need to traverse the whole grid. Step 2, when you see the first letter of the word during step 1, you want to explore its neighbors with DFS. Step 3, while exploring its neighbors, you want to keep track of the index of the letter that you're currently looking for in the word so that once you've reached the end of the word, you know that you found all the letters in the board and you can simply just return true for this question. Alright, so now let's take a look at how to implement this solution. So to begin with, we're going to create this visited 2D array, and it only contains Boolean values, and we initialize it to be containing a bunch of false. So false for range, length, board, 0. This, I'm gonna do it for range, length of the board. And then we're going to start traversing through the whole grid to see if we could find the first letter in the word. So for I in range, length, board, for J in range, length, board, 0. If board ij is equal to first letter of the word, then we're going to explore its neighbors. But before doing so, we need to update the visited value of this current cell. So visited of ij will be set to true. And then we will need to explore its neighbors by using this backtracking technique that we talked about in the explanation of the solution. So let's first create this backtrack method. And this is going to contain the row and the column number of its parent cell, and then the index in the word, and then also the board and the visited graph. So in this method, the first thing we're going to check if the index is equal to the length of the word minus 1. So the index that we are passing into this method is the index from the level above. So if that index is at the end of the word, that means we're done with all the searching and we found all the matching letters in the grid. So we could just return true. And then we're gonna explore all the directions. I'm going to create another variable over here just so we could use this directions easier. So 0, -1, 1, 0, then -1, 0. And I'm also going to pass this into the method so that we don't have to create this directions array every time when we need to run through all the neighbors of a certain cell. So right here, I'm going to, for dx dy in directions, we're going to get the current row. It's going to be row plus dx, and then the current column is going to be column plus dy. Then the next step, we're going to check whether or not this current location of the cell is inbound. So if current row, 0 less than or equal to current row and less than the length of the board, and 0 less than or equal to current column less than length of board 0. And we also going to need to check whether or not this current cell is visited or not. So and not visited, because we don't want to use the same letter cell twice. Current row, current cell, no, current column. And the last thing is we need to check whether this letter in the cell is the same as the next letter in the word. So if board current row column is equal to word, and we need to +1 on the index because we're looking at the next letter in the word. If all of these conditions are true, then we set the visited at this location to also be true, meaning that at this point, we believe that this current letter cell is going to be one of the cells that matches the letter in the word. So true. And then we're gonna run this backtrack method on this cell so that we could explore its neighbors. So if self.backtrack, and we're gonna pass in this row, column, index +1, same word, same board, visited, and same directions. If this thing also returns true, then we return true. So when would this line return true? This line will return true at the end of the word. We've found all the matching letter cells. And if not, then we need to set this location's visited status back to false, meaning that from this location, there's no correct answer, there's no correct path. So we could just stop. All right, so the backtrack method is done. Let's go back to the main method. And right here, we have set the visited of ij to be true. The next step would be explore its neighbors by calling this self.backtrack method. For row, we're gonna pass in I, and column will be j, and then index would just be 0 because we're always passing in the parent cell. So the parent cell in this case is 0. We're just starting from the word. And then the same word, board, visited, and directions. And if this line returns true, that means we have found a path in the grid that contains all the letters in the word. So we could just simply return true right here, meaning that this word is in this grid. If this line does not return true, that means at least from this current ij, we cannot find a path that contains all the letters in the word. But that doesn't mean the board doesn't contain any path that would match the word. So we're just gonna set the visited of ij back to false. But after this for loop, when we have done traversing through the whole grid and we still cannot return true from any of the possible paths, then we return false, meaning that the word does not exist in the board. Alright, so that is the solution. And as usual, let's talk about runtime and the space complexity of the solution. For the runtime complexity, since we're traversing through the whole board, so the runtime definitely has this size of the board, so m times n as part of it. And then inside of this traversing through the whole board, we're calling this backtrack method. And say in the worst case scenario, for every single one of the cell in the board, it is indeed the first letter in the word, then we need to call this backtracking method on every single cell. And in this backtracking method, when you're exploring the cell's neighbors, we are only going to explore 3 neighbors because one of the neighbors is definitely the neighbor that we're coming from to reach our current cell. So say if in the worst case, when you explore all 3 neighbors and all 3 neighbors contain the next letter in the word, then you have to go explore their neighbors. And if their neighbors are having the same situation of having the next letter in the word, and if this condition continues till the very end of the word, then you have to go down the length of the word levels, which makes the runtime 3 to the power of L, L being the length of the word. So in total, the runtime for this solution would be big O of m times n, the size of the grid, times 3 to the power of the length of the word. And for space complexity, since we're creating this visited 2D array to store the Boolean values for each cell in the grid, that's going to be a big O of m times n space complexity. And also, when we're doing the recursion for our backtracking method, the worst scenario would be going down L levels, L being the length of the word. But L is never going to exceed the size of the grid. So in total, the space complexity for this solution is going to be big O of m times n. Alright, so that's it for today's video. I hope you enjoyed the solution. Please give this video a thumb up if you found it helpful, and feel free to leave any comments down below if you have any questions or comments or concerns, and I will see you in my next video. Bye!